Hi, my name is Selassie Dumenu, and this is my final video exam presentation on data analysis for ENGI 305. A quick overview of what we're going to be looking at in this presentation. We're going to be talking about a total of 10 concepts dealing with data analysis. The first one we're going to look at is ANOVA, which is known as the analysis of variance. Next, we're going to look at bivariate analysis, reliability and survival. We're going to delve into design of experiments and see what that is all about. We're going to define and explain what hypothesis testing is, look at chi-squared tests, then try our hands on some control charts, and then specifically look at the Pareto chart. Then next, we're going to look at logistics regression, and then finally, we'll be talking about the graph builder. So, ANOVA. The analysis of variance is usually used to test the differences between group means. It's usually calculated with the Fisher distribution, or the F-test, as it's properly called, and then significance is usually determined based off the p-value and a confidence interval. Input variables in this method are usually categorical, and response variables tend to be continuous. And let's say a real-life example would be, let's say if you had to test the differences in 4 treatments and yields of tensile strength of fiber, for example, which means now you have 4 groups. And what usually happens is that we test the difference within the groups, and then we test the difference between the groups. To better understand this, we're going to switch over to JUMP, and then we're going to be dealing with the analgesics data set. And we're going to show how this method or this test can be conducted in JUMP. Alright, so now that we're in JUMP, we are going to go ahead and look at the ANOVA and see if we can conduct an ANOVA test. But first we have to go and get our data. We can get our data in the JUMP Pro by going to sample data, which has data sets available. And when we go, we can either just open it by categorized by types of analysis, which will probably be faster. And here we want our analgesics data. So I'm going to go ahead and open that. Alright, so we see 3 columns here. We have gender, drug, and pain. And we're going to be running a model for this. Alright. So first we go to analyze. And then in analyze we have our fit y by x. And we have a response and then our x, which is our factor. We're going to go ahead and put pain in our response. And then select drug in our factor. Alright. Go ahead and click OK. Oh, even before that, one thing you see here is that with one-way ANOVA, it shows us the 4 types of graphs that we could get from running this fit y by x model. And as you can see, this is what the one-way ANOVA looks like. This is logistics, contingency, or chi-squared, and then our bivariate. But we are hoping to get a one-way ANOVA from this. So this is our guide. And so if you get something that does not show what the one-way is supposed to look like, you know that maybe you have your factors put in wrong, or you know that your graph is completely off, or your plot is off. Alright, so blow this up. What we immediately see is data points for drug A, B, and C, and the pain from 0 to 15. And we notice that drug A has consistently lower scores than the other drugs. And then the x-axis are also unequally spaced. The length between the ticks are proportional to the number of scores or observations of each drug. And you can't really see much from here. So usually when you want more information, we go in here And then if you, let's say, hit your means or ANOVA, what you see is that you see these triangles pop up on your data. And then what that does is it also gives you summary of fit, your analysis of variance, from which you can draw your conclusions. And basically with this model, we see that the analysis of variance report shows the probability is greater than F, or the probability is greater than F, and that is 0.0053, and that in terms supports visual conclusion that there are significant differences between the groups. Another thing you can check with these is that you see that in the summary of fit, you can see means, sample size, standard error for each level of factors. So this is basically how the ANOVA test looks like, and this is a one-way analysis of pain by drug, basically. So yeah, this some of the things that you would be looking at, and this is how the plot or data set appears. I mean, there are multiple things you can do here. You can add quantiles if you prefer that, and take off the means or ANOVA. And as you can see, the quantiles show your whiskers in your box plots. Another thing you can do is, you can compare means, you can do an equivalence test, you can check your power, you can change your alpha level, so you can try and generate your CDF plot, densities. So yeah, it's pretty extensive, and it's a good tool for analyzing data. Alright, so up next we have bivariate analysis. Now, bivariate analysis basically checks relationships between two continuous variables. And then, unlike univariate, which deals with one, bivariate is bi, so as the name deals with two. It's a very simple form of quantitative analysis, whereby it's very simple to do, and then it generates a scatter plot for which you can fit a line or mean, and then get all your results or information from. We're going to be using the SAT dataset and SASJump to show how this is done, and then further explain how useful this method can be. Now, the way that this whole presentation is going to work is that these slides are going to just give us the brief and general ideas of what the methods do or how useful they are. And then when we go into SASJump, we can go ahead and delve into detail a little bit by demonstrating actually what and how they can be used. Alright, so now we're going to look at bivariate analysis in JUMP. And we have to go ahead and get our SAT data. We can do that again by just going to the sample data index, because we already have that open. And if we open up our bivariate analysis and we go into the data set, we look through, we don't see any SAT data. Alright, so what we can do now is go into the full list, and that is, you see it by alphabetical order of all the sample data files. When you click on that, the data set that you're looking for will be alphabetically. So if we go into the S column, I believe that our sat data will be right there, and that is sat data right here. I'm going to open that. So that is another way to find your data sets in case they're not categorized by the type of analysis. So if we open this is very extensive. We have 51 rows and a lot of columns, 23 columns to be precise. So again, you see subplots, tree maps, parallel plots, graph filter maps, graph filter maps with column masses, and those are already models that have been created. So usually when you just run the script, they will pop up, but we want to see how to actually go about the process. So first thing we do is we go to analyze. Again, we go to our fit y by x, and then for this we are going to select 2004 verbal as our y, and then the percentage taking 2004 as our factor. So when we see our 2004 verbal, that becomes our y. The percentage taking 2004 becomes our factor. As you can see, bivariate here shows that the data set is nominal against nominal. So we should, again, like I was saying with ANOVA, this is a good guide, so that gives us sorry, I said normal, I meant continuous. This data is continuous, not nominal. It's continuous data. So when we click OK, it gives us a bivariate fit of 2004 verbal by percentage taken 2004. Again, what we see a lot of data points, but one thing we can see clearly is that the percentage, when the percentage was small, the scores were actually higher than once the percentage went up. When that is, you can notice that off because it shows a downward slope as the population increases or the percentage taken increases. So one thing we can go over here is go into the options, and then these are basically fitting commands. So if we want to fit a line, a regression line, see, I'm going to scroll up here. This regression line shows the downward slope, which is that the numbers actually decrease as the population increases. And then a good, you see your linear fit here, and your R-squared values, adjusted root, means of, and then we see another analysis of variance here. So we can actually try and use ANOVA in this case as well. So we can go and then fit a spleen if we wanted to. We can fit the mean if we so desired, and that is represented by the green line. That's a straight line across. As you can see, most of these points are not centered around the mean, but all the same, it's a very good model because one thing we check with our R-square values is that we want that to be as close to 1 as possible, and this one is giving us a value of 0.79. Okay, so next we have reliability and survival. Now, like the name says, reliability and survival basically deals with lifetime and failure analysis. I mean, on a broad scale, that's basically what it does. Then there are various forms of conducting reliability and survival tests. You know, we have the life distribution, recurrence analysis, degradation. We have survival, just to name a few. And then one term that we usually come across with reliability and survival is censored data, which usually Census data is data that might not necessarily have all the points available, and some of them is being held back. So it's not like a full data set, but it's censored in that sense. And the common distributions when dealing with reliability and survival are the log normal, the exponential, and the Weibull. And then to demonstrate this better in JMP, we'll be using the size and power dataset. Alright, so now we're going to look at reliability and survival, and we're going to go into our sample data index, and then look at our reliability and survival down here. Let's go ahead and pick the FAN dataset. Then we see we have 70 rows, 70 sets, 70 points or 70 samples. And then we have 5 columns here, which is our timer, sensor, exponential, Weibull, and extreme. Alright, so to conduct a reliability and survival analysis, we just go into analyze. Then here we see our reliable and survival. And like I was saying in the PowerPoint, there are various methods. We have life distribution, fit life by X, recurrence analysis, degradation, reliability and forecast, reliability growth, reliability block diagram, survival, like just there are so many ways to conduct life analysis. But we are going to be using the life distribution in this demonstration. And then what we're going to do here is that we're going to put our time and make that our Y, time of event. We're going to put our sensor in the sensor column and run this. Put this here. Sorry. Alright. Okay, so when we run this, we get our life distribution window. And as you can see, we see all these distributions here. So we can compare like log normal, a Weibull, then a logistic. Good thing is that they're all color coded. So if we see this one seems to spread out more, the Weibull, and then the log logistic seems to the second, which is widespread, and then the log normal. And if we were to take these off and just check the lines, we can do this as well. So let's say if we went with these and then we click on this, you see the data points for that. See how centered they are around the line. If we had a logistic and then we click on that, take the Weibull off, we see how those are centered around the line. And then if we wanted to see the scale for log normal against that same distribution, we see how that, and then you see that the numbers here or the distribution profile change for each of them. So if I go to a Weibull now, then come down here and click on this, see that we have a 0.188, and then the time now goes to 5975. We have summary of data down here. If we want more information, we can open that up. It shows us our observation used uncensored values and then the right censored values. Then we come down to our profilers, which is our distribution profiler. Quantile profiler, hazard profiler, density profiler. And if you come into here, we have some more options. You can show survival curves, you can show quantile functions, you can show hazard functions, you can have an interval type that is for more advanced and depending on the models that you're trying to determine. So this is a very it's very extensive. You can get as specific as you would like it to be, and a good way with determining models between distributions is to look at the AICC and then the BIC models. AICC is RKA keys. Yeah, the AICC is the K keys, information criterion corrected. That's the low C. and the BIC is the Bayesian information criterion. So basically the lowest, the one that gives the lowest AICC, and BIC can be attributed as being the best distribution in this case, and that is how we differentiate between the model comparisons. Okay, up next we have design of experiments, or DOEs as they are usually called. And this is probably one of the more important aspects or methods, or if we can use the word again, experiments for improving quality and productivity basically across the board in basically any business or production facility, company, it uses factors and responses to generate the most favorable or desired factors to achieve a set goal. The word trials runs is a major part of this, because they're like experiments, so you have to run them a number of times to generate the numbers that you will need for the various factors, or to be able to come out with the most optimized process or the most desirable result. So that is a major part of the process, and then they can be conducted in various forms. They are basically a lot of custom designs that you can do, and each of them are tailored to meet the type of results that you are looking for, or the type of test or experiment that you want to run. So they can be screening designs, there's response surface designs, full factorial designs. You can have mixture designs, Taguchi designs, they're nonlinear designs. So it's a pretty broad, or there are a lot of options to choose from based on the specific goal that you're trying to achieve. And we will thoroughly go over this in JUMP to show how you can use these different designs and what each of them are more tailored to. Alright, so for our design of experiments, we are going to go into our sample data index, then open these by close this up, open our type of analysis, then here we see we have a lot of data to choose from, and we are going to go ahead and then do a couple of these. The first one we'll go ahead and do will be our bounce data. Okay, so we go ahead and blow this up, and let's say if we wanted to run a model and run the script here, see that our report fit model is already generated because of the script has already been generated for us. We see our software Selene and our RS and our Silica. Just go ahead and run this, and basically we want to see our stretch. What are the problems of our stretch? You see our R-squared value here of 0.99, basically a really great model. Our probability also shows it clearly. We see our parameters, effects test. We see the ones that have the highest effect and the ones that have the least ones. Then the current stretch here is not the most optimal. This is due to the default settings. So what we want to do in this case is we go ahead and then when we maximize our desirability here, it goes ahead to show us the settings that we must adjust our factors to in order to make sure that we get the highest possible stretch. So it basically runs these tests and knows, okay, you have to put our Silica has to be at like 0.98, our Selene at 47.566, and then our software at 2.04 in order to generate our best stretch response. So this is one form of design of experiments. Now let's say I want to conduct another design of experiment, but this time let's go ahead and do a Taguchi array. I will go ahead and then get the data for that. So I'll go into my sample data index. Then let's use the Brian Taguchi data. Click on that. Load that up. I have my Brian Taguchi data. If I go ahead and then try and analyze this data here, I'll click the right. When I run it, it'll give me my fit model here, and I have all the necessary Y and macros already inputted in here. We don't need to change any personality or emphasis. And this is what I get when I run that. We have our least square fits. Then we have our response SN ratio. Which shows our depth, adhesive wall infer, and we have a summary of fit. We have a parameter estimates for each of the results that have been generated. Right, so I can take this a step further by trying to generate a prediction profiler. And I believe that if I go into my response mean Y, I should be able to locate that. And here you see my prediction profile is here. And so next up, we have hypothesis testing. This is basically a method of proving or disproving results, or inferences about data or quantitative research. You usually have a null and an alternative hypothesis. The null hypothesis is the true statement or the belief, and the alternative hypothesis is what experiments are showing or what we think might actually be the case. Now, they're usually calculated using the standard normal distribution, and then rejection and acceptance of the hypothesis is based on confidence intervals and p-values. We have some data in JMP that we can run and then test hypothesis using some of the tools available in JMP, and we will do that in the next slide. Okay, so to conduct a hypothesis test in JMP, we can go ahead and then create a table. And so we go ahead and create a new data table. And if we say that a number of people say they were born in, let's say, Virginia. Right, born in VA. And then this will just be our number. So if you have a number, speed, let's say 1. We have 1 and 2, right? So we have yeses, say 1591. People say we're born here, and then 59. That gives us a total number of 150 as our sample. And then we have our continuous, and then our nominal value, nominal data. Okay. So if we want to conduct a hypothesis test in here, what we'll do, we can go ahead and then do that by using the distribution option in Analyze. So we go ahead and click on distribution. We're going to use our columns, which will be born in VA. Then it'll be frequency number. What that gives us is a distribution here. Go ahead and then switch this and make this vertical to make it easier to read. And gives us our probabilities, our counts, and our total, like I said, which is 150. So we see our yes, then our no. So let's say we want to create a 95% confidence interval. We will click on the red button here. And then we can go down to confidence intervals. And if we say we want a 95% confidence interval, click on that. And that shows us our lower confidence, upper confidence for our no's, and then our yeses. Alright, so let's say we want to go a step further and then test our probability. We'll go test our probabilities. Then we have our no and then our yes probabilities from our confidence intervals. Let's say we want to say that it's 0.5. So half for all. Alright. And then it's very important that we select the hypothesis that we're going with. And then we're going to say that this is a two-sided. So we're saying it's not equal to, or that there is no difference. Then when we hit done, we see our likelihoods and our Pearson, which give us our probability greater than a chi-squared for our Pearson and our likelihood. And then, right, so what we see right off the bat, what we can infer from these two tests is that the probabilities match, because you see this is a 0.0087, which is basically the same as the Pearson, which is a 0.009. And what we can conclude from that is that the p-value is small enough, which indicates that there is convincing significance from the data. And this is how we would basically conduct a hypothesis test in JMP. Alright, so up next we have the chi-squared test. And this is a statistical test applied to categorical data. And again, categorical data is usually either pertaining to like race, gender, educational level, etc. And the main aim is usually to test likelihood of any observed difference against the expected. It uses the chi-square distribution in its calculations, and then significance is usually determined using p-values, critical values, and chi-squared values. So if we look at a quick example here, and say Brianna wishes to test whether education level is independent of gender, and she now collects data from 100 randomly selected people in New York City. Now, what we first see here is that we have two categories here. Educational level is one of them, gender is another. Now in gender, what do we have? We have male, female, which are the two, common gender types. And then educational level could be uneducated, GED, bachelor's, master's. So those are the kind of scenarios whereby the chi-square test will be a good test to use to try and test any likelihood of differences. And when we move over to JMP, we'll actually have a detailed data set, and that'll be the carpool data set, and that is what we will be using to show how this is done and what the results might mean, or why it will be significant. Alright, so to demonstrate the chi-squared, we're going to go ahead and then find our sample data, and the one that we want to use for this is the carpal data. So again, if we go into our alphabeticals, find a carpal, click on that to open it up. Blow that up to see all our columns and rows. We have 303 rows and 6 columns. So sex, marriage status, age, country, size, and type. And as you can see, these are all categories. So besides age, which is continuous, you see most of these are just nominal. So to create a contingency or a chi-squared, go into analyze, have a fit y by x. We can use size as our response in this case, and then have country as our X factor. And I got trusty contingency back here, down here. See, we have nominal and nominal, which is going to give us a contingency. So if we go ahead and click OK, what we expect to see is a contingency table. But then again, this is our mosaic plot. Our contingency table is down here, which we will be doing our reading or analysis from. And immediately you see that it gives us a count total column and then a row. So when we analyze this right here, we have our probabilities down there for our likelihood ratio and our Pearson test and our chi-square values. And then again, our probabilities are low, which indicate a very strong or convincing significance. So what is one way to read this? For example, let's say if we wanted to, one thing we can actually see straight off the bat is that there are not a lot of large Japanese cars, because as you can see here, the count here, the total count here is 42, and the number of Japanese cars in the large column, just 2, not a lot of large European ones as well, with 4, and then the majority being the American, which is 36. So another thing, let's say if we wanted to see how many European medium-sized cars we have, then again we come to European, then the second column here is medium, so we match that here, and then as you can see we have 17. So if we wanted to see the total number of Japanese cars, we just go across, we check the large, medium, and small, come to a Japanese column, and then we see that we have a 148 right here. And what is the total percent of that? It constitutes 48.84% of the total number of cars. And that's basically how we read our contingency table and how we see it, what the differences and likelihoods are. Up next we have control charts, and this quality and process method mainly aims to evaluate and improve results using charts, and feedback from key variables helps show when a process is either in or out of statistical control. There are various types of control charts. I've listed only 4 here, and because these are not the main ones, but they're basically the most common ones that you will come across. And they're basically they're also Shewhart charts for variables. So the first one is the X bar chart, and then the X bar chart basically deals with averages or displays subgroup means. The R chart mainly deals with ranges, which is basically maximum minus minimum. The P chart usually shows proportions, and then the C chart, which is for control R, shows lower and upper control limits, or displays control limits. Another one that usually common is the S chart, which deals with standard deviations. We're going to be using the socket thickness dataset in JMP and then we're actually going to build some of these charts and then see how they're done and what the results will look like. Alright, so for our control chart, we're going to be using the socket thickness dataset. So I'm just going to go into alphabetical listings and then see if I can find that here. And that is the quality control data. Open this up. You notice that we have our rows, which we have 400, and then we have our 6 columns that we are going to be dealing with. Alright, so let's go ahead and then go into our quality and process. We do that by going into Analyze. Here we see our control chart builder, which we can just click. Now we see that gives us our window, and we are going to drag our thickness into the Y zone here. See, that is going to give us a Y zone right here. Then we add our hour, drag our hour to our subgroup. Take our subgroup right here. Then what we quickly see is our lower and upper control limits. And then if you see our C chart variables up here, we see our points, our connected lines, our statics, limits, points, 0.2. Then it'll go down to limit 2 and our warnings, our 3-way charts. So basically more specific details. But our thickness summaries are right here. It shows our upper control limit of 11.68, our low control limit of 7.78, and then our range, which is 4.49 for our LCL, our UCL of 17.20. Now, if we just looking at the average chart, we see several points below the lower control limit of 7.78, and we can go a step further and drag our cavity into phase. And when we do that, we now have our averages and then our range of all 4. You see our X and our chart of thickness here. So we're looking at 2 out of our 4 that we mentioned in our PowerPoint slide. And this is basically how we can use the chart builder. And whenever you're done, of course, you can just click done, and that'll generate the chart that you want. Have a few options here. You can get your limits, save your summaries, and you can show the control panel, which will take you back in case you need to make any changes. So this chart builder is very efficient because instead of just generating an X bar chart and an R bar chart separately, we have 2 charts here we can compare and then work with off the bat. And again, it's key for letting us know our control limits and then to test which points are out of control and see if we can change that or improve on our process. Alright, so up next we have the Pareto chart. And if you're thinking that Pareto is a very interesting name to assign a chart, that is indeed true. And just like most mathematical equations and physics laws, this chart was named after an Italian engineer, sociologist, and a philosopher, and his name was Vilfredo Pareto. And this chart basically deals or shows frequency of problems in quality related process or operation. It is good in helping either managers or business owners or even industrial engineers to decide which problems to solve first by highlighting the frequency and severity of the set problems. And it usually comes in the form of a bar and a line graph, where you can see the representation in descending order by bars, and cumulative total are represented by the lines. And now there's something called the 80-20 rule, which was once again associated with Vilfredo Pareto, because he was, I guess, the pioneer in developing this principle, which stated that 80% of your output comes from 20% of your resources, or that 80% of your effects can be attributed to 20% of all causes. And that is basically the rule of thumb when it comes to most businesses. And again, the Pareto chart is very useful in helping you know what you need to attack now, or proper allocation of resources to guarantee efficiency. We will be looking at this more in JUMP, and we will be using the failure data set to do that. Alright, so for our Pareto chart, we're going to be using our failure data set, and then going to go to our trusty alphabetical listings here, and then look for that data set. It should be for the F, data's R, so we have our failure here. On that, very simple data set, we have our failure, and then we have our N. Again, we already have our script here, which is our Pareto plot, but we're not going to be doing that since we want to be able to go through the whole process. We're going to do that from scratch. So we're going to open our Analyze, go into Quality and Process. As you can see, we have our Pareto plot here. And then when we click on that, we have just two columns. We have our failure, and then we have our N, which will go into frequency. I'm going to go ahead and hit OK. See that it gives us our Pareto plot, and we see our bars and our line, like we were talking about in the PowerPoint. Alright, so how would we interpret this? We see the count of failures, which is the left axis, and then the right is the percentage of failures in each category. See our bars are in descending order, and the curve, which indicates our cumulative failures from left to right in increasing order. So if we go ahead and then try and, let's say, make this more detailed, let's go in options and see what options that we have here. Let's say if we want to show our percentage points, see that our lines are our points up here across. Which will help us to, further determine the percentages, or make it easier to see the cumulative percentages at each point. we have one more. We can go ahead and label our accumulated percentages. So if you can't actually tell, now we have the actual numbers here. And then we know straight away that contamination definitely needs to go down, because it approximates about 45% of our failures. So this is the general Pareto plot, and based on how specific or how general you want it to be, or how detailed you want it to be, detailed is the word I'm looking for. We can use all our options here to show all our, basically, to generate all the numbers that we need, and that'll help us determine which area we need to focus on to make our product or our process more efficient or better. Yeah, so now we have logistics regression, and then it examines relationships between, categorical and continuous variables. Nominal logistics and ordinal logistics are two forms, and nominal regression estimates a set of curves to partition the probability among the responses. Ordinal models the probability of being less than or equal to a given response. And then with regression, it basically examines relationships between variables. That's generally regression. And then there's linear and logistic. And people kind of think these are the same. People kind of get these confused. But, with linear regression, one thing you can look at is just when you take the outcomes, for example. Linear regression, the outcome or dependent variable is continuous. It can have basically any one of the infinite number of possible values. Whereas with logistic regression, the outcome or dependent variable has a limited number of possible values. And then whenever we plot these with the linear, just in the word, it's a line. So when you plot these, you see that with linear, it's a straight line, because it's mostly comparing this thing. Most times it's dealing with two. But with logistics, what we see with logistics is that they appear in the form of an S-curve or a sigmoid curve. And then dependent variables are binary or dichotomous. And when we say dichotomous, we basically mean that there is some level of branching or division into two parts. And when we head over to JMP, we'll be looking at the penicillin data set to run some logistics regression, look at our results, and then analyze and see the importance of this method, or why this method is useful in many cases. Alright, so for logistics regression, we are going to be using our penicillin data. So we're going to go ahead and pull that up. You should find that in our P. Alright. And then we see that right here. Our penicillin data, we'll go ahead and open that up. So we notice our 4 columns and our 10 data points. Now, we see that the logistics regression has already been made, but we are going to once again go through the whole process. So we go to analyze, fit y by x, and then our responses, we're going to go in our response. Our indos will be our x factor. And then once again, we have our guide. See that when we have our nominal in our y and then our continuous in our x, we're expecting a logistic. This is the S or sigmoid curve that we were talking about in the PowerPoint, which is what it's usually represented by. See our iterations, our R-squared value, our k keys, our Bayesian, parameter estimates, just to name a few summaries. And this is a fitted model, which shows basically a probability of being cured. And so if we go down to our parameter estimates here, we see our intercept and then our probability of 0.0011, which is significant, indicating that dosage amounts have significant effect on whether the rabbits are cured or not. If we want to make this more detailed, we can come in here, we can plot our options, we can show our rate curve, we can show our ROC, which is our response category, and then we can lift the curve. We can show our odd ratios, our inverse predictions. And this is basically what the logistics regression plot looks like in JUMP. Alright, so now we have the graph builder, which is the last method that we're going to be looking at in this presentation. And the graph builder is pretty straightforward. It is used to interactively create and modify graphs. Graph types include bar charts, pie charts, histograms, maps, contour plots, just to name a few. And then we can examine and illustrate relationships between several variables in a graph. This is one of the methods where we can pick apart in JUMP, because we can actually go through and then with one data set see how we can generate different graph types using this method to really show how efficient it can be. And once we head over to JUMP, we'll be using the Candy-Bars data set to do this. Alright, so finally we are on to our graph builder, and we're going to be using our Candy-Bars data for that. So we go ahead and then find our Candy-Bar data, which we should find in our C category, or in our C alphabets. We have our Candy-Bars right here. You can blow this up because, as you can see, it's a pretty loaded data set. It has 17 columns and 75 rows. So if we go into our graph here, and then we click on our graph builder, as you can see, these are all the possible graphs and plots that you can get from JUMP. But we want a platform that will allow us to build different graphs based on interactively dragging columns into graph zones. So it's not really graph specific, it's interactive. So as we come in here, we will start by dragging our total fat grams into our X zone. You see here, total fat grams, and then put our calories in our Y. Alright, and what we first see is our scatter. This is our points, and then we see our smoother, which runs through that. What you see is a line of fit. We see an ellipse, shows a bivariate normal density. We have our contour, our line, which gives us the response summarized by categories. We have our bar graph, have our area, box plot, our heat map, and then our caption box. So based on basically the data, the categories that we're using, these are the options that we can generate. Now this is a histogram, but we can't generate that, and that is why it's not available to click. So if I wanted to, instead of a smoother, if I wanted a line, here you see that we have our summary of fit right here. And then it'll show our linear regression with confidence intervals. If I take these points off, you see a straight line. Leave the points on. If I put the points back on, take the smoother off, all you're going to see is a scatter plot. Now if we want our ellipse here, you can see that. If we want to generate a box plot based on the same data, we can. If you just wanted a graph showing the bars, we can do this as well. If we wanted a heat map, it goes ahead and then shows us the heat map. If we wanted just a line fit, we can have that as well. So it's very interactive, and it basically generates a lot of options. And if we were to, let's say, add an extra category in here, like cholesterol, let's see, if we put cholesterol in here, what does that do? Put that in the X zone now. Group X. And then we see that it now gives us our cholesterol in grams. If I were to put a smoother in here, see our smoother. If we want our line, see all our line fits for each of the cholesterol options, not options, but of the cholesterol levels, is 0, 2, 3, 4, 5, 10, 15, and 20. Then if we go a step further, and if we remove cholesterol, let's say we want to go ahead and remove cholesterol, that'll give us our regular scatter plot back. So let's try that right now. Right click, sorry. So let's say I go ahead and now drop cholesterol into the overlay zone. Now we see our cholesterol groups have been separated by color and points. This is just a way to show how interactive the graph builder is, based on, you know, where you put the data, or where you put the factor or the column that you might be considering, and how it's interactive based on that. So whenever you're done, you click done, and then you have your final plot. And there are options that you can use after that, which is categorized by your theme, your legend, position. And if you always want to go back, you can just show your control panel, and that'll take you back in case you need to take away a factor or two.